All right, today we're going to talk about data visualization and data exploration. Before I get started though, okay, so the rough outline of the class is that we're going to talk first about the basics of visualization. Then we're going to talk about data types and visualization types. And I'll finish with just a brief description of software plotting libraries. There's going to be one that we use pretty much entirely, which is Matplotlib. And I am going to actually try to hopefully go through an example in a notebook because there are just a lot of sort of code snippets I'll be showing here. I'll just do it in a notebook instead of in the slides today. It's a question, yeah.
Are we done with like all the database?
So we're done with all database stuff. Moving right along. There's going to be a homework. So the question was, are we done with databases? Yes. So this is a brief overview of these things. There'll be a homework assignment on databases, and so you will learn a lot more and explore a lot more with queries and this kind of stuff in the homework. But the idea is the lecture and notes try to give you sort of the basics as well as a few more references, and then you will practice that on the homework. So yeah, we're done. You know databases, right? So yes, not to learn anymore. And we're going to do this especially at first when we talk about different types of data. So graphs, free text later, geospatial data. We spend one lecture on each of those, right? So that's on the website, right? So they will come back, certainly. We're going to use these concepts later. But yes, the idea is that we have, fairly quick sort of blitzes on each different topic. The analytics part we spend a lot more time on. That's, I think, because those things are, there's a little bit harder to grasp in one lecture, I think. Also, I'm biased. I work in machine learning, so admittedly. But for the most part, yeah, we jump around pretty quickly. Okay, so I want a few quick announcements, though, first of all. So again, trying to sort of clarify a couple things on the homework assignment. So apologies if this is obvious to you. But we've had several people submit code saying it runs locally, submit to Autolab, and there's a clear sort of error in the function. So runs locally does not just mean you can run every cell in the notebook and it does not throw an error. When you define a function in Python, it won't actually call that function, of course, right? So if your cell runs, it doesn't mean it's actually running. When we say runs locally, we mean it doesn't throw an error when you execute the cell, and you can input the test data that we give you, and it gives you the output. So you have to do both those things when we say run it locally. I think that's sort of clear to most people, but there was a little bit of confusion there. Especially if you haven't had much Python experience before, that might be a confusing thing. Python will be very forgiving in what it lets you do in a function before actually executing it, because it doesn't check anything until you actually run that function. So when we say run it, we don't just mean execute the cell, we mean run it on a test case. The second thing is we're going to put up a Piazza poll. I know now that the ad deadline's over, now it's time to switch between 388 and 688 for those that want to. And I would really actually encourage a lot of people to do this if it feels appropriate. So essentially, if the XML parser just seems incredibly hard to you, and maybe you don't come from a CS background, it's a good sign that maybe if you can get credit in it and don't want to spend a very large amount of time on these assignments, you should consider switching to the 388 version. We will make room for that now, and we'll also have an option for people watching on video to be in 388 while still also being in an online sections. If it's necessary. Hopefully it's not necessary, but if we need to, we'll do that. And likewise, if you're a CS undergrad and this all seems easy to you, please do think about switching to the 688 version. You'll get the more units. And I think a lot of people sort of find it very useful to work on the more kind of programmatic and challenging assignments. So please consider doing it in both directions. But we were going to put up a Piazza poll not a poll, really a thread where you can just sort of say your name, and then I'll resolve it as we submit them. We can kind of do it in batch, so I actually would prefer people just sort of submit in batch rather than coming and talking to me every time. I mean, I'm happy to talk too, but it involves, we have to send emails to the various admins here to switch you over. Sometimes these signatures, sometimes not, depending on your department, so we'll sort of work that all out. But now's the time when we start working it out, so we'll start dealing with it now. If you are in 388 and intend to switch, just do the assignment for 688, and you should be all set. And also today I happen to actually have to run off after class right away, so I can't stay to chat after class with anyone. So just know I'm going to get out very quickly, but it's not. If you want to come chat, let's chat just next time after class. The rule, which I even forgot last time, but people then reminded me, was that we are trying to make the first, I think maybe even 2 rows in the class not have laptops, right? If you're doing it today, you already sat down, you might have forgotten. You can do it today. Let's just try. I'll try to keep remembering, because a few students mentioned that to me. And if you can try to also remember, maybe just the first 2 rows. I think that's maybe all the demand will have. But first 2 rows of class, maybe no laptops. The last thing I want to mention is that on the course website. Let's see. Okay, so on the course website now, and I also, I warned you, but I was even worse than I intended to be in terms of getting up the notes, but I'm not yet behind a full lecture, is the good news. But one thing I wanted to point out, which I didn't do last time in the Jupyter lab, was so we have, the slides, the notes for class, and the notes, like for last time's class, goes through the ideas of databases. It goes through, the ideas of the different relationships, and then has the code that actually sets up all the examples I had from last time. Incidentally, it turns out I found out what the issue was, because I knew I had run that code. I forget who pointed out to me that there was 2 equal signs instead of 1 in my code. SQLite actually allows you to use 2 equal signs in SQL code. So it's not valid SQL as normally is, and no other engine would do that. But SQLite understands that they're used by people like me that forget to do that, and so they actually allow 2 equal signs. So that's why the code ran while still having 2 equal signs. Anyway, this is all the code there. The thing I want to point out is that the notebook, the notes will all have this link up top that says download it as a Jupyter notebook. So you actually can download these same things as Jupyter notebooks. So I prefer the HTML form for just reading. I think Jupyter notebooks are actually very long. This is not really conducive to reading, I think. You can if you really want to. But if you want to actually execute them, this is all code. So all the code is right there, and you can just execute it and do things like that. So it's hopefully a handy resource to have if you want to go through the actual content we work through in class, all in notebooks. And I am so far, 1 lecture behind always, and I'll try to catch up a little bit. It's a busy season right now, and it will get a little bit lighter in a second, in a few weeks. But hopefully no later than I am right now in getting these notes up. I think that was all I had to mention about that. Let's. Okay, so if there's no other questions, let's just jump into visualization. Oops. All right, so let's talk a little bit about the basics of visualization. When I do that, though, I want to distinguish between 2 types of visualization that I think are often kind of lumped together, but it's really important to distinguish these 2 things. The first is data exploration visualization. So this is the visualizing you will do when you encounter a new data set that you're starting to work with, that you haven't worked with before, and you want to understand the data. Right? And so that sort of the emphasis there is on quick views of the data, functional looking at the data from a functional standpoint. And basically figuring out what the right visualization is to get the most information, for you to extract the most information about your data. The second type is data presentation, right? And this is once you've analyzed the data, you figure out what there is in there, and you want to make your case to convince someone that this point is there. You make a nice, pretty visualization that illustrates that point. These are actually 2 very different things. The emphasis in the first one is going to be on you getting the understanding, and the emphasis in the second one is going to be on broad understanding very quickly, right? So you can invest more time, and the aesthetics matter much less in the first one as long as you understand things, but the aesthetics matter much more, and there has to be a much clearer story in a way in the second one. What I'm going to focus on for the majority of this class is the first one. We're going to have a little bit on presentation, touch on these topics at the end of class, and maybe some of the final lectures, but it's really not the point. We're not yet making the PowerPoint presentation or the web app that will convey these points to the world. We are worried right now about you understanding the data to begin with. And so that's the focus we're going to have on visualization. And of course, the other point is that data exploration as a whole is much broader than visualization. Visualization is an important part of it, but it's just one piece of a much bigger puzzle. And really, almost everything we're going to learn in terms of analytics or machine learning or any kind of analysis actually could be seen as part of data exploration, or at least part of it can be used in data exploration. So just be aware of that there's this distinction here, and we're talking about the first one when I mention visualization for the most part. Now, the importance of visualization really cannot be overstated to a certain degree. And this is a point I sort of see again and again in practice in data science, is that people that have just learned about machine learning, they download some data set, and the first thing they do is try to apply a machine learning algorithm to it. And that's almost never the right thing to do first. The right thing to do whenever you encounter a new data set is to plot it. Just plot whatever you can, whatever information that there is in this data set. Try to figure out a way to visualize it. Because without understanding your data, the chance that you can code some machine learning algorithm or apply some machine learning algorithm to understand it is almost nothing. So always, the first step of any data science pipeline, really, when you get new data, should be to visualize that data in some way or another. And the other thing is that if you are trying to do things like prediction of your data or trying to build a predictive model, the other reality is if you can't visualize that thing you're trying to predict, chances are you're not going to be able to predict it. So chances are if you can't plot your data in a way where you can make the predictions that you want, a computer algorithm will not be able to either. We hear a lot, I think a lot sort of conveyed about superhuman AI and kind of algorithms that can discover things that no human ever would. But the truth is that's the exception, not the rule. In the vast majority of cases, what algorithms can do is they can do exactly what a human can already do, maybe slightly worse, but a whole lot faster and at a whole lot larger scale. Right? So you can identify trends in many, many more data points and many, many more records in your data. But that's not something you couldn't identify yourself if you spend a lot of time with one instance of your data, right? So just be aware of that. And this is sort of why it's so important, is that unless you can see and identify what you're trying to do with your machine learning algorithm or with your big data sort of analysis of any kind, you're not going to be able to actually accomplish it with some learning algorithm. And then I really can't hammer this point home enough, is that this is the goal of data science, is not to replace humans, it's to just do kind of a rough pass at what we do, just at a much larger scale. Okay, so the next thing I want to emphasize is the difference, the importance of visualization above and beyond just statistics of the data. Here I mean statistics with a small s, not the field of statistics. I mean things like the mean of the data. It's a statistic of the data, right? So if you have some data, say a bunch of points in space here, you may be tempted to summarize that data with, the mean, the standard deviation, and the correlation. Of course, this is, as you might imagine, a very imperfect form of summarization. So this is I think the last time I taught this class, someone posted this on the Piazza page. I thought it was a very cute visualization of what I mean here. But here, there's going to be an animation of data points where at every frame in this animation, the data points have the same mean, I guess up to this significant digit. The last ones here, if you see them in gray, they're actually changing a little bit. But to a first approximation, it has the same mean in both directions, same standard deviation in both directions, same correlation in both directions. But the data can take on very different things. Can look like very different things, right? So it's going to, all these points are moving around, becomes a little dinosaur. I thought that was silly, but kind of clever. Of course, this is a mathematical property, right? Those are 5 numbers describing many numbers here that describe each point. So of course, we can find multiple instances of these points that have the same numbers there, right? This is just a mathematical property. And so you're never going to get a full view of your data if you're just looking at statistics of your data, by definition. I mean, they're helpful precisely because they are more compact representations. So if you can find a way to actually visualize the whole thing, it can be very, very valuable. All right, any questions so far? It's fun to ask that when there's a little dinosaur animation on the screen. All right, this is from some Twitter post. I actually don't even, it was again pointed out to me in the last iteration of this class. Okay, so let's move on to talk about data types and visualization types. These are things that I had always, for a long time in machine learning, I had encountered these things, but never actually had a name for them because I didn't go, they're covered oftentimes in kind of basic stats courses, but I had never encountered these names until well into my PhD. And that I found that it was really nice to actually be able to kind of categorize data in this way. And so it's very useful, I think, to sort of know these terms. They're sort of standard terms in statistics, but they're really quite useful. So the thing I want to start off with now is enumerating different types of data. And the types we're going to consider, they're very odd names, I should add. I don't like these names. They're not the ones I would necessarily use, but these are the names that are given to them. So you should know these things. The data types, the 4 data types people always talk about are nominal, ordinal, interval, and ratio. Who here has heard of these types before? Okay, so like a third of the class maybe, which is about what I expected. They're not always taught, despite the fact that people can analyze data for a long time, you're not always taught these things. Okay, so this is different types of data you may encounter. And it's doing it for, in computer science, we think of data as being, well, it can be floating point, it can be integers, it can be strings, this kind of stuff. But really, this is a more conceptual, what is the data type really behind these data points? And this comes in these four categories, and they're distinguished by the types, I think most formally, they're distinguished by the types of operations that can relate different instances of data types. So let me say what I mean by that. So the first type are nominal, which are categorical data types. These are things like a pet could be a cat, dog, or a rabbit, right? Those are just categories. There's no notion of continuity between data points. They're not like real numbers. You can't take half a cat and half a rabbit as a pet. Doesn't make any sense. They're discrete entities, and there's some usually finite number of these things. Okay? So that's categorical data types. And the other thing that's important about categorical types is that there's no ordering to these things. There's no notion to which one pet is greater than another pet or less than another pet. The only comparison you can make between between nominal data types is equality or inequality. So if I have 2 data points, each of a nominal type, that means I have 2 examples that take on the value dog, cat, or rabbit, etc. Say just there's those 3. All you can say is, so x is one of those and y is one of those. All I can say is x equal to y or is x not equal to y? That's my only comparison point between those. Okay. Moving one step sort of in the hierarchy of richness of the data, we have ordinal data, which is also categorical data, but unlike nominal data, it has an ordering associated with it. So for example, and I'm actually using this example intentionally of numbers here, if we think about ratings as a data type, so you guys are well into using Yelp already, or if you've familiarized yourself with the intricacies of the Yelp API and exactly what it returns. One thing it returns is ratings, right? And ratings are 1 to 5 stars. But I would argue, and Yelp kind of disagrees actually, because Yelp averages ratings together, which I think is not always the right thing to do. But I would argue in most cases, ratings are actually not really numbers. They're really kind of relative, discrete chunks, right? So, there's no real notion of the average of a 1 and a 5 being the same as a 3. Or the difference between a 5 and a 4 being the same as a difference between a 4 and a 3. Right? They're just sort of conceptual points where all anyone can ever really agree with is that 5 is better than 4, 4 is better than 3, etc. And of course 5 is also better than 3. So there's an ordering of these things, but there's no real notion in which they're describing real concrete numbers. They're just a discrete set that has a ranking associated with it. And here, the important part is that you have more operations you can apply now to these data types. So if I have x and y, both of which are nominal, sorry, I keep saying that, both of which are ordinal data points, I can again say is x equal to y or is x not equal to y, but I can also say is x greater than y or x less than y. Notice I can't do things, which I'm going to do later, like add or subtract them, because it doesn't make sense with something like ratings. They're not actually numbers. You can't say that, again, the difference between 5 and 4 is the same as the difference between 4 and 3. All you can do is say that, yes, 5 is greater than 3, and 5 is greater than 4, right? Any questions so far? Yeah.
When we talk about the rating system, isn't that, I mean, when you say 5 is greater than 4,
Yeah.
but can that not be different for different users? For example, if somebody is a very, if a person is not one guy who gives out ratings very easily, and for example, I'm a strict person, and
Right.
my code
Yeah.
would be equal to yours.
So the question was sort of, isn't it possible that users have very different definitions of these ratings internally? So one person gives 5s to every restaurant, one person gives 5s to everything, and one person gives 3s to everything, and is very rough. So that's fine. That's definitely true. That can actually be true for almost all of these things, actually, that different people could sort of have different means and biases in terms of their internal data they will give. That's fine with all of these. That's not really the point. The point is that no matter who the person is, a 5 is still better than a 4 for everyone, right? It should never be the case that someone feels that I really like this restaurant, so I'm going to give it a 4. A 5, that would be much worse than the 4. That should be the one thing everyone agrees on, is that there's a strict ordering of these things, even if, of course, people differ in their means or their mean assignments to things. But that actually can be true for a lot of these things as well. That can be true for a lot of the data types, is that, if you consider them as personal, if people are prescribing these from their personal opinions, they can, of course, vary over different people. Yes?
Sorry, I still don't quite understand what's the difference between the third one and the last one.
I'll get to those now. Yeah, I haven't described them yet. Okay, so interval is the next type. An interval is really about a numeric. Interval is really a numeric data type. So interval data is now real valued data. And actually doesn't even have to be real value data. The important point is the operators of add and subtract actually matter for real valued data. Okay? So if you use something like the one everyone uses for it's actually really hard to think of interval things that are not ratios, so it's not that easy. The one everyone uses, which hopefully makes more sense in a second, is temperature. Degrees, and in particular temperature degrees Fahrenheit. And it's important that I'm saying Fahrenheit there for a reason I'll get to in a second. But anyway, Fahrenheit makes sense in terms of addition and subtraction to a certain extent, right? I can say that the difference in some sense between 10 degrees and 20 degrees is in a very concrete way the same as the difference between 20 and 30 degrees. There's a real sort of mathematical relation there where these make sense where it makes sense to do things like add and subtract them. So a difference of 5 degrees is a difference of 5 degrees. That can be, between 90 and 95, or these days it can be between 30 and 35, right? Those are the same kind of thing. I mean, of course, we might experience them differently, those different things, but those are the same types of differences. In other words, it makes sense to have operations like add and subtract. There actually are cases where these can still be discrete numbers, but in general, what it really means, you can think of them normally as sort of real valued, and what it really means is that there's a fixed, the intervals between data points have some real concrete meaning. They aren't just abstract things where there's some ordering between them. They actually have, they kind of lie on an actual number line effectively. Okay. And the last one is ratio. And these two are always the hard ones people kind of get confused by. But the ratio is also numerical data. But the difference with the ratio is that and the way it's sort of put is that 0 has a special meaning in ratios. It's an awful name, by the way, ratio. And the reason why is that it allows this division operator, which you don't allow here. And the example that absolutely everyone uses to describe the difference here is the notion of temperatures Kelvin which is a ratio number, versus temperatures Fahrenheit, which is a interval number. So in Fahrenheit, 0 has no real meaning. And what this means is the following. If I have the degrees 10 degrees Fahrenheit and 20 degrees Fahrenheit, there is no notion in which 20 is twice as much as 10. Right? Because 0 in Fahrenheit is some arbitrary thing. There's no real meaning to 0 Fahrenheit. I mean, it means something, like something freezes at that temperature, but there's no real meaning to it. You can't say something is twice as much if it's twice as large in degrees Fahrenheit. On the other hand, temperature Kelvin is a real physical quantity. Right? So it's actually saying that this is a measure of the energy inherent in the molecules. Right? So if the temperature from 1 to 2 degrees Kelvin, there is a real sense in which there is sort of, I don't know if it's actually linear like this, but maybe say twice as much energy, or maybe some nonlinear version of that, but twice as much energy, say, in the 2 degree Kelvin as in the 1 degree Kelvin. All right, so that's the important part of ratios there, is that 0 kind of means nothing. I mean, as in 0 means nothing of the no quantity of something. Whereas intervals, there's no notion of 0. It just, all that matters is the relative rankings in this number line. Most data that's numerical you will have will be ratio data. It's actually hard to come up with examples of interval data that is not ratio data, but they do exist. And it's important for this reason of sort of the ability to divide. So, as I said, 20 degrees Fahrenheit is not twice 10 degrees Fahrenheit. I can't divide temperatures Fahrenheit and get a meaningful quantity. I can, however, divide temperatures Kelvin and get a meaningful quantity. So ratio is really special in that it allows for this kind of division, for saying something is X times as much as something else. Right? And this is sort of very common. These two, again, don't often, when it comes to visualization, you don't often differentiate between these two. But when it comes to the things you can do to operate on the data, it's very important. All right, so let's have a few polls now of examples here. The first poll is going to be about nominal and ordinal values. And so for each of these cases, the thing is either nominal or ordinal. You should check it in the poll. Let me just open the poll. Check it in the poll if you believe it is ordinal, and leave it unchecked if you think it is nominal. Keep reloading and keep connecting to the wireless again. All right, 10 more seconds. Keep loading, keep refreshing. Reconnect to wireless. CMU, CMU secure. Do whichever one is better. I'm gonna close it in 10 seconds. There's another one, so if you miss now, you get to answer the next one. All right, gonna close it now. Okay, so let's take a look. So for the most part, the answers are clustered around what you would think of as sort of the common answers here. So gender, that definitely is just going to be nominal, right? There's no notion in which there's an ordering of the different gender options. One is not greater than the other or less than the other. They're just different options that are equal or non-equal. The responses are equal or non-equal. The next one is income. So this, I would also say is definitely, not also, I would conversely say is definitely ordinal. Because here, even though, there's no sense in which really, and I should say, it's not like anything, these things are value judgments. That's not really the point or anything like that. The point is that there's a clear sense in which there's an ordering there, right? There's this one is less than this one, by definition, which is less than this one, right? So this is going to be an ordinal data point because we know that everyone in this category makes less than the people in this category, right? And that's sort of a classic ordinal problem or ordinal data type. The third one, I think everyone got, or most everyone got to be ordinal. That is sort of almost the classic example of something that's ordinal but not numeric, right? It's the survey response of how much do you agree on this. If you really agree, you say, I strongly agree, and everyone agrees that strongly agree means more than slightly agree, but of course no one knows how to compare those two, right? Does it agree, strongly agree mean more than agree, strongly, or slightly agree and neutral? No one knows. But it's clear that there's a ranking there, so this is sort of in some sense the prototypical ordinal data type. And the last one is also, I would say, probably most recently thought of as being nominal too. That one actually could go either way, depending on the purposes of this survey that people are putting out. They could say, like, we really want to find people that are going to say yes, that's our goal, and so we're going to, especially be treating it as if that's a higher quantity for some reason than the other one. But I think for the most part, you would say that would be, you wouldn't go that route. So the point is that binary responses can, in some sense, be ordinal if we feel that there is a inherent ranking between those two. But for the most part, I think the majority of class is right here, and that you would typically consider this to be nominal as well. Any questions on that? Okay. Let's do this next poll now, which is the same thing for interval and ratio values. So let me open that one up. So here it says, which of the following are ratio? Oops. Okay, got it back. Which of the following quantities are considered ratio quantities? So check them if they are ratio. Do not check them if they are interval. So there's length in meters, length in feet, velocity in meters per second, and IQ. All right, we'll have maybe one more minute. couple more votes this time, so someone managed to get in that didn't get in last time. All right, closing it now. All right. Okay, so I'm actually interested by those first two. So for length, actually, would someone care to speak up either way to argue why, for either one actually, why length in meters and length in feet are either nominal or ratio? Yeah.
They're ratio because like 2 meters is actually twice longer than 1 meter.
Right? Yes, so that's correct. So actually, I'm curious that I mean, you don't have to maybe. I hate to sort of ask people of this when after I've given away the right answer, but the one that sort of voted for those being interval, want to explain the logic of that? I know that's a daunting question to ask. That's way too much.
I did because I did not understand the difference
Okay.
between ratio and interval.
Okay.
So I just what I see.
Okay. But velocity was ratio. Okay. Any other sort of thought? So in general, I'll say yeah, there.
For me, I thought that like zero didn't have like a real like value. I guess it didn't have a true zero for like length.
Okay. Interesting. So zero wasn't sort of special in some way. Yeah. So I think I would say sort of. I guess I would think of it as being special. Zero length. That means there's no length to it. It means it's nothing. But I think that actually the point, the other response, which was, and I guess sorry, I always forget to repeat it on the video. So the answer is that the first three typically are in fact ratio, and the last one is in fact integral or interval. And I actually really liked the comment there, and then that's actually the test I use as well. Is does twice of something mean twice as much? Does two of something mean twice as much as one of something? Right. So is 2 meters twice as long as 1 meter? Yes, clearly it is. And that implies that zero has to mean something, right? Whereas 20 degrees is not twice as hot as 10 degrees if you're thinking about Fahrenheit. In no sense is that true. So I think that's sort of the difference I would have there. And similarly for IQ score, for those that don't know, IQ is one arbitrary intelligence measure, but the point is that the mean of IQ in the population is supposed to be 100. So there's no real notion. Zero doesn't matter. Zero is just some number away from 100. So there's no notion in which you're twice as smart as someone if they are. Rather, if someone's 100 and you have an IQ of 200. For whatever that actually means, which is probably actually very little, but there's no notion about it being twice as smart or anything like that. It's just some arbitrary scaling with actually a mean at 100. So that is a good test, and I like that test of does twice as much, does two of something mean twice as much as one of something? But yeah.
So based on the definition, then would Celsius be a ratio?
So the question is Celsius a ratio? Actually, who? Thoughts? Do you think it is?
I thought it was because just like 0 Kelvin means something, right? So 0 Celsius is like the freezing point, and it's like a linear offset from Kelvin, like 73.
Yeah. So in general, Celsius would not be considered a ratio. It would still be an interval. So the fact that zero, again, and this is why it's probably an odd thing, but it's always phrased that way, of zero having a special meaning. But really it means that zero means none of something. And in Celsius, it's just a different scaling of the temperature. But it's not as if 10 Celsius or 20 Celsius is twice as hot as 10 Celsius, it's not as if 10 Celsius is infinitely more hot than 0 Celsius. For Kelvin, actually it is. 1 Celsius is infinitely hotter than 0 Celsius or 0 Kelvin, which is actually no energy at all, right? It isn't, and this is why I sort of had the feet. At least a couple people said maybe feet is interval and meters is ratio. It's not about the unit of measure, the system, is it English versus the metric system. It's about, does the 0 point mean nothing effectively, and can you think of ratios in that quantity having meaning, which is why the name is called ratio. Yeah.
I think it's kind of weird to not consider like Celsius and Fahrenheit to be ratios, because like you can convert Celsius to Kelvin just by minusing 2 centimeters.
Right.
So like there's a linear dependence between Celsius and Kelvin. So
Yeah.
it's that like maybe like for example for Fahrenheit after conversion, it's not that 2 times like 20 is not twice as 10 degrees, but it's still like something linear.
Yeah. So I think the question is that it seems odd to use temperature in this sense, because they're, even though, yes, it's not truly, a scaling linearly 0, it is still an offset, a linear of Kelvin equals Celsius or Fahrenheit. And that's true, but it does, that linear offset on both of them does destroy the specialness of 0. And what 0 means. 0 does not mean none when you have that offset. And so you can't form ratios of the two, and those are not meaningful. The fact that you can then do an inverse linear transform to get that one doesn't undo the fact that in natively Celsius or Fahrenheit you can't. And so this is why these things have some sort of use. I'm going to move on now. I think this is about visualization. Ultimately, I spent a lot of time talking about data types. But the reason is that the way I'm actually going to present visualization is one more question, maybe.
Yes. So just a question about ratio. The slide you showed that you can divide but not multiply. Is that?
Yeah. So there's no notion of multiplication still here in any of these things. Doesn't really know. Even temperature Kelvin. So the question was, can you multiply these things? And temperature kelvins doesn't really make sense to multiply those, right? Division, the point is you get a ratio, you get a dimensionless quantity for these things because you're dividing one unit by the same thing. So it always should be a dimensionless ratio, a number. Multiplication would be like that quantity squared. It doesn't really have any meaning. Like degrees squared, I don't know what that means. Whereas ratios, those are unitless by definition, so they actually have meaning regardless of your units. And so that's why that is actually has some value there. All right, maybe one more. So the question was, do ratios exist for vectors? Yes, you can have vectors that just have multiple quantities. A vector you can think of as sort of a combination of multiple different data types, one for each dimension. And so you could have types that are different. You have ordinal vectors, right, in some sense. In the notion of vectors like a direction in space, they kind of have to be numerical. And 0 does have a meaning, so that implies a kind of ratio. But vectors in kind of the sense that we're going to talk about them, which just mean collections of multiple points of data, can be any type you want. Yeah. Yeah. Okay, yeah. So So I think that maybe I should just have said speed there. That wasn't the point of that. Yeah. Okay. So what I want to move on to now is finally visualization types, and the reason. Let me get this. Okay. And the reason why I actually spent some time. Come on. Okay. The reason why I spent some time on data types is that I think most discussion on visualization kind of are a little bit more sort of abstract in terms of what the plot chart or visualization is trying to convey at some fundamental level. So what is the what are we trying to show in this visualization? And I'm actually not going to cover that too much. What I'm going to cover is and I think it's actually an important way, just before you get to the point of what do you want to convey in this plot, which is I think much more along the lines of data presentation than it is about visualization. I think what's equally important and a common mistake I actually see is just doing a correct mapping from data types to the appropriate visualizations that support those data types. So what I'm going to sort of consider is data that comes from different types, like nominal, ordinal, has the interval and ratio, right? And also has different dimensions. So maybe I have my first dimension of a data of a point is ordinal. My second dimension is ratio or something like that. How can I plot data like that? Because a lot of different types of data of plots, what they're really doing is they're just providing means of visualizing different types of data, and then they sort of depend on what. Depending on what the dimension of the underlying data is, you have to use different types of plots. So I think it's really worth, whenever you create a figure, and if you don't do this, by the way, I see some really bad things, like categorical values that are plotted as scatter plots, right, and things like this. It just don't make any sense. So I think what's actually most important in visualization to a first approximation is just to make sure that your visualization maps correctly from the type of data you have to the visualization you're using. I know that sounds really basic, but it is a mistake a lot of people make that haven't sort of had real training in visualization. And so as data scientists, I think it's very important to have some basic concept of just what visualizations are allowable. So let's go through this now. And in particular, we're going to cover these following ones. This is not by any means an exhaustive list. I will also try to show some of these in Matplotlib, which I introduced briefly last time. But all the plots here I'm going to show are generated in Matplotlib, and the notes for this class will have the code to generate all of them. So just know that even if I don't get to all those, you'll still see the code in the notes. So I'm going to also differentiate here between 1D, 2D, and 3D, and potentially higher D data. And what I mean by that, when I say a 1D data, I mean I have a collection of data points where each point is either 1, 2, or 3 dimensional. Right? So when I talk about 1D data, say interval 1D data, what I would mean is that I have a collection of data points where each point is a single scalar number. That could be an example of a 1D data that has ratio data. And in general, most of the things we do here are actually not going to differentiate between the two questions we had, which are ordinal and nominal, and ratio and interval. But of course, the difference between categorical and numeric are very important. Okay. So let's just jump in. I think this will hopefully be a little bit more explainable when I actually get to some examples. So let's talk about 1D data. 1D data really can be either categorical, meaning in this case ordinal or nominal, or it can be real valued, meaning interval or ratio. And depending on this, there are really not that many, but a few choices of charts you can use for this. So if you have categorical data and it's one-dimensional, what you want is you want a bar chart. Right? Because everything else doesn't actually make any sense. Just tries to convey some information that isn't actually there. So this example, I actually can't, let's see, so I have 10 plus 3. So I had 20 data points here, right? 10 of those I know are dogs. 3 of them are rabbit, and 4 of them are cat. Remember, I have 1D data. That means each data point has to be either dog, cat, or rabbit. And the way I summarize these 20 data points is with this plot. Right? This actually conveys all the information. I can tell you exactly. I can't tell you the order. We're saying the order of the things doesn't matter here. We're going to say you can always rearrange your data set however you want. But modulo order, this chart conveys everything you need to know about your data set. In fact, I could reconstruct it already. I know I have 10 dogs. I know I have 3 rabbits. I know I have 7 cats. Now these are sort of suggestions. These aren't absolute rules here about what's allowable where, but they are pretty, they're strong suggestions. So for example, one thing I frequently see in charts like this is people drawing lines between the top of bar charts, which is for this data completely meaningless, because there's no notion of anything that happens in the middle here. There's no notion of what it even means. What does that mean to show a line from dogs to rabbits, right? It doesn't mean anything. There's no notion. I mean, you could rearrange these things. There's no ordering here. If it is ordinal, maybe a little bit, there might be some rationale for saying, okay, I'm kind of treating it as if they were real value on the x-axis, so I'm going to kind of draw these lines, but still it's probably not the right thing to do. But certainly with categorical, with nominal data, there's absolutely no reason to draw lines between the tops of bar charts because there's no ordering here. So don't do that. So in general, this is kind of the suggestions that I would make about charts like this is don't include information that is not consistent with the data type that you're actually showing here. Okay, the next type of chart I'm going to say is a pie chart, which should never be used for any type of data. Pie charts are horrible. They convey information very badly because humans are really bad at looking at charts like that and figuring out ratios. Our visual eyesight does not compute that, the actual ratios. I mean, all it conveys is ratios, right? It doesn't convey absolute numbers at all. So it's strictly less information in some sense than the one before. And actually, we're also sort of provably much worse at figuring out relative sizes even from this than we are from the previous picture. John Tukey, who was also this famous statistician who has a lot of these great quotes about visualization, also has a quote, which I should have put on here, but it says that something like anything can be done in a pie chart can be done better other ways. So don't use pie charts. Yeah?
But this tells you like the portion of people that own each pet, right?
So okay, the question was, this tells you the portion. So I could take this and I could write on this 50%, 15%, and 35%, right? That would convey exactly the same information and actually be better because you are better at picking out relative ratios in rectangles than you are doing it in a chart in pie slices. I don't know why. I mean, pie charts someone liked them at some point, but they should never be used. Yeah.
I'm not fully convinced. Like, I mean, when I see the one, I can see, oh, half of the animals are dogs, whereas here, the half of the animals are dogs and they're cats. It's just over a quarter.
Yeah. Okay. So the question is sort of, in this one you can maybe see that half the animals are dogs. I would say maybe you could do that for half. That's probably the one case in which you can actually do a good job of that, maybe when it's half exactly. Other ratios, people are very bad at estimating from wedges. By the way, I've used pie charts in plots before, so I'm not innocent in this endeavor myself. But for any other slice, we're really bad at it, and maybe 25% too. But for other slices, we're really bad at it. And if you want to convey that information, just label the plots with that. It will get at the same information. We understand percentages, and it's better than trying to figure out, if I have two things on different sides here, for example, it's very hard for us to know if they're bigger or smaller. We just are very bad at doing that, and so it shouldn't be used. This is a little bit more of a suggestion, but I would still, there's very few cases where you really want to include a pie chart in your, despite and definitely don't do the Excel thing where you have like a 3D pie chart that's a wedge coming out and it's with perspective. Definitely don't do that. It's just the worst way of presenting an actual result. Okay, last 1D data illustration which you might care about is for numerical data. Is a histogram for numerical data. So a histogram essentially takes my numerical data and it bins it into certain interval bins. So it kind of discretizes it and then forms a bar chart that over that discretization. Now importantly, the x-axis here actually is a real valued quantity, right? So it would make more sense. You shouldn't necessarily do it, but it would make much more sense here to draw lines between the different points because the actual intervals do, have meaning here. So it would be reasonable to draw lines. But histograms are amazingly useful because they convey information about distributions that we are really bad at seeing any other way, right? So when you have 1D data here, every point is just one number, and when we want to understand something about the distribution of these numbers, the best possible thing you can do is plot the histogram of those numbers. So whenever you have any amount of data that you really want to be familiar with, plot histograms of the individual features even if you have high dimensional data, plot histograms of those features because it's very, very illustrative and it will help you understand your data to know what distribution it comes from. Much more as I said, like at the beginning, than just the mean or the standard deviation, right? The mean or standard deviation does not tell you the actual shape of these things. It just tells you, the average of them, which is much less information than the actual distribution themselves. This is a Gaussian distribution. It's what we always think of when we think about histograms. But most data is not like this, actually. And knowing that it's not like this will actually help you in understanding what your data actually looks like. OK, so let's move on to 2D data now. Again, 2D data, what that means is that I have a collection of data points where each data point has two values. It has like an x and a y coordinate, effectively. But you shouldn't think of it as x and y. That implies actually something visually. It has an a and a b coordinate, right? So let's think about a few sort of simple examples here. If both values here are, if both elements of the data are real valued, probably one of the better things to use in a first pass is a scatter plot. Again, I know this is probably obvious in hindsight, but people don't always do that. People use like bar charts or something else for these things. Somehow, just plot if you have two-dimensional data, plot as a scatter plot. Now there are sort of failure modes here. So if you have too much data, to the point where you can't get a sense of the actual density here versus over here, maybe. It just becomes like a mess of dots no matter what. You've reached a failure mode of scatter plots, and don't use that anymore. I'll tell you, I'll get to what you could use in a second. But for most small size 2D data, a scatter plot is incredibly useful. One question I sort of get is, couldn't you use ordinal data for scatter plots? And the answer is yes, you can. What happens with the ordinal data and scatter plots is that you're kind of because ordinal data is usually limited to a certain number of positions, you're basically going to get it's much easier to reach that failure mode of crowding your data too much. Right? So the only reason this kind of works visually is because I can kind of see that there's more data points here than there are on the outskirts, right? If I only had 3 possible values for each of these things, I would not be able to tell which of the values, had a lot, positions had a lot of data points, not very many data points, because they'd all be overlapping at the same coordinate. And so the reason why I would say not for ordinal is it can be fine, especially if you have a lot of categories. But in general, the failure mode of scatter plots happen when you start overloading sort of the density, the space you have in the plot, and that happens much quicker for ordinal data. Another type of plot which can make sense here, and actually I should probably allow this one to be ordinal a little bit. Maybe it has the same issue potentially, but maybe that one makes more sense, are line plots, right? And so these make sense if one of the dimensions is clearly ordered. Or so if your data points sorry, I shouldn't say that. This one makes sense if your collection of data points comes in some ordered fashion. So thus far, everything else I've been describing, there's no notion of real ordering to the data, in that there can be, for this case here, there can be many y values that all come with a similar x value. The difference with a line plot is that one of the dimensions, at least, is only going to be sequential. So time, for example, in your data point, I don't have an example here of time being one thing and then time being here and then time being back there. I don't have 2 outputs for the same time. For every time, I have one output exactly, and we also expect there to be some continuity over time. So there's a little bit of a deviation in that you have to sort of also think about now, not just what's the type of data, but also is there some sort of inherent uniqueness to one of the coordinates, and we expect there to be smoothness in the other one coordinate from the other coordinate. But if that is the case, and it's most often the case in things like time series data, then a line plot makes the most sense. But again, the actual structure of the data here is that this works when both the coordinates are numeric. Otherwise, it doesn't really sort of make as much sense. So again, why not ordinal in the first dimension? Again, that one makes a little bit more sense actually to include. I could have included that one because something like time really could be considered an ordinal quantity. But a good reason not to use this for ordinal either dimension is the same thing I mentioned before, is that with ordinal data, there is no notion of equal ratios, meaning similar things. So if this was an ordinal quantity, there would be no sense in which this interval here is the same as that interval there. And what that means is things like the slope of this line would have no actual meaning, right? Because this interval here could mean something very different from this interval. And so the notion of the slope of this line at different ranges wouldn't actually have any meaning. And it's very hard for us to sort of ignore the meaning of something like slope. So that's why it's probably not good to use it when the first coordinate is ordinal, but not actually an interval or ratio. Any questions on that? That one's a little subtle, I think, because there's two distinctions going on. You first have to have both real value data, but they have to be of a certain type, where one kind of is inherently sequential. And then you have to also, there has to be sort of a unique mapping. There can only be one output really from multiple, there can only be one second dimension for each first dimension. Okay, any questions now? All right, so let's sort of, again, keep moving right along. If you have one of the dimensions of data is ordinal, and the other one is real valued, there are actually a lot of options here, but something like a box and whisker plot is kind of a good option here. So what these convey, and actually there are better ones too, but this is sort of gets at least some of the point. So if you have categorical data on one axis and numerical on the other, the best thing you can do in some sense is to split your data by the categorical variable and then somehow visualize the data over that split for each of the numerical categories. So this is a graph of weight for animals of different types. All of this is all just made up data, by the way, I should emphasize. There's no real, I have no idea. I mean, I'm not looking up real dogs or anything like that for this. Okay, so why is that sort of what you should do? What we're trying to do here is we're trying to understand, what do the real valued numbers for this one look like versus these ones? If I were to run something like a scatter plot here, you would get this failure mode where you have a bunch of overlapping data points here, a bunch over here, and you wouldn't really be able to see it very well. So this is sort of the next best thing after that. What this does is a box and whisker plot draws essentially the mean, or sometimes median, depending on who you ask. Actually, I think median is much more common. So it draws in the middle here the median, the usually 75th and 25th quantile, and then the 5th and the 95th quantile, and as well as plots just the individual outliers. So this is essentially what this shows here is different quantiles of the data, and it acts like a very, very rough estimate of a histogram. Over the numerical values corresponding to the different categorical variables. That's what a box and whisker plot is listing. Now you could argue that that's actually a really poor histogram, right? That's a poor approximate histogram where I was just telling you how you want to look at all your data and you're sort of throwing it all away. And whether you want to use this thing or something called, there's more complex things called like violin plots, which actually show, the actual histogram of these different things, often symmetric, so it looks sort of pretty and that kind of stuff. You could use that if you want to as well. That gives you a better sense of the distribution of each of them. But the point is, no matter what you do, what you want to do is you want to break apart the categorical attribute and then provide some sort of summary of the numerical attributes for each individual categorical variable. Right? That's going to be the goal of all of them. Any questions there? Yeah.
Excuse me, how do we calculate the length of the rectangular there?
Yeah. So this side. So right. So the standard for, and I should have checked this actually. I believe, from what I remember, the standard for a box and whisker plot is that this line here actually is the median. So it's the median statistic. This line here is the 25th percentile. This is the 75th percentile. This is the 5th percentile. The 95th percentile, and then these ones are here are any points that lie outside that. So they're kind of the outlier points. That's just a sort of rule of thumb. People do other things as well, but it's just sort of a basic illustration of some of the quantiles of your data. Percentiles, really, yeah, but yeah. Okay, and I'm not going to have time. Looks like to go through too much of the code, but let's just get through the actual visualizations because I think it's still important. And the notes will have all the code to generate these things. As I said, these are all just plots that I generate in Matplotlib. I'll show a couple of them maybe at the end before we end. Okay, so a heat map, which is actually not a great visualization, but can work okay sometimes. If you have two categories that are both categorical, if you have two dimensions that are both categorical, now you need something a little bit more than what we had before, because if I run that as a scatter plot, it's going to be meaningless because every point, there's only going to be 9 points, they're all going to be points. You can't tell which has actually more than the other. So a heat map essentially says, what's the sort of relative amounts of different things. So the color codes it by some and it shows you the relative amounts by color coding, essentially. So I'm guessing here that yellow is a lot and dark red is very little. This is sort of okay. I probably should have also put a little legend here showing the relative scales of those things. And it's good because what this tries to convey is this conveys the relative amount of each of these different sort of cross products that you need to convey, because otherwise you sort of wouldn't be able to do that. You could also have circles that show where the size of the circle indicated how big each of those was. But the point is you break out each possible combination of the categories and you show something that indicates how many elements are in that cross product of categories, essentially. And yeah, there's a question over there. Sorry, what's your question?
Rabbit, dog, and dog, rabbit in both locations.
Right, so the question is the rabbit, dog, and dog, rabbit have different things. That's perfectly fine. Heat maps do not have to be symmetric. There's no reason for them to be. These are just two different categories. I mean, I'm using the example of a first pet and a second pet here, so I guess the idea here is if people get a rabbit, they're going to get a dog next. But if they get a dog first, they're not going to get a rabbit second. That's what this is saying. The number of people that have their first pet being a dog and rabbit is bigger than if they have their first pet being a dog and second pet being a rabbit. Again, all made up data, but that's what it conveys. But again, there's no notion of symmetry here. These are just two different categories, and I'm just breaking down and illustrating the size of each individual bucket here. And this is actually not to be confused, though, with a different kind of heat map. So this is called a heat map, but this is sort of a heat map for categorical variables. And it shouldn't be confused, though. I mean, it's obviously very similar, but it shouldn't be really confused with a heat map, which is really trying to show density of real valued variables, i.e. sort of a 2D histogram. So if I take real valued variables and discretize them, like I did with a histogram, but do it over 2 dimensions now, and plot that as a heat map, that's essentially a 2D histogram of the data, right? So I'm building a histogram where the color of each point indicates how many points are in that bucket, where the buckets are now divided up by 2D chunks, 2D little squares. The important point here is that this type of heat map, also called a 2D histogram, the ordering matters very much. Right, so ordering is really important here, whereas in this case, this is just categorical data, so the ordering does not matter of these things. I'm just conveying sort of the properties of two different sets of categories here, whereas the other one, this one, of course, really does matter. Now, in some sense, this is just sort of a much more finely discretized version of the last one, where order does matter, but they are sort of conveying different things fundamentally. The other one's trying to just show sort of the magnitude of different cross products of categories. This one's trying to show effectively a 3D figure where the height kind of each location here that would come out if you're trying to make a 3D histogram is encoded by its relative color. And those are sort of the types of data plots you typically use for 2D data. Again, because we sort of went through all the combinations of both being real, one being categorical, and then both being categorical. And I do want to add that this one, you could replace those colors there with like sizes, circles that sort of show how big they are, or something like that. Though again, with the issue that people are not very good at judging relative sizes of circles, so you have to be a little careful with that.
People also really bad at judging relative shades of colors.
Yeah, so the question was, are people also really bad at judging relative shades of color? That's absolutely true. I actually left it out here, but you probably should include a legend with these things so that people can kind of place the colors in a linear scale and have some sense of size. The reality, though, is that we're not great at this, visualizing this no matter what, so there's probably going to be a little bit of inaccuracy that comes along with your figure. All right, so let me briefly now mention 3D data. And maybe if I run out of time here, maybe I'll just mention some of the code next time in class. We actually have a specific overflow lecture where I can that I've intentionally left so that if some lecture goes long, we have that option. Okay, so the first thing about 3D data is that if you have 3D data, say that that's all real value, what most people do is they plot a 3D plot. And just like a pie chart, don't ever use a 3D plot with the following caveat. So it's absolutely fine to do a 3D plot when you're doing kind of your own exploration of data. My guess is you will not find it that useful. But if you have a 3D plot where you can kind of, rotate it around, get different views of data, if it's an interactive 3D plot, that can be okay. But a static 3D plot is awful because this tells you nothing about what the data actually looks like because it's not a 3D surface we're projecting it on. We're taking a 3D plot and we're projecting it onto a 2D surface, which means we lose any information about what the data actually looks like. We just have no idea, right? Because we're only looking at it from one angle. So it actually is not even defined. I mean, it's ambiguous what this data even looks like because we have no way of knowing, where in depth in this dimension or this combination of dimensions each of these points lies. So in general, if you're trying to convey, certainly if you're trying to convey results, don't ever use a 3D scatter plot. If you're trying to explore the data yourself, you can, but only an interactive one, and you probably actually don't want to do that anyway. What you should probably do is a scatter plot matrix. So scatter plot matrix, what it does, this is if you have, and this is actually the same data as before, and you can see much better the actual different types of data. What a scatter plot matrix does is it takes all 2D possible combinations all two combinations of dimensions and shows a scatter plot of those. So I have these scatter plots here of every 2D for the first and the second, first and the third, and second and the third. Those ones there are just the transposes of these. And on the diagonal, those are sort of the same thing on each dimension. So that on the diagonal has histograms, 1D histograms of each feature. Now, I will say something else here. These can be nice for data exploration. I think they're actually equally bad as 3D plots. Maybe not quite as bad, but they are equally bad for data presentation. So this is very dense in terms of the information on this plot here. And if you are willing to be exploring your data and trying to figure it out, that's fine. You can invest the time in to get all sorts of very deep meaning from plots like this. You can say, oh yeah, no, I know that the second feature is this thing and has this nice pattern of correlating with the first one, etc. They are fine for exploration, they are not at all fine for presentation. Because it's like just like throwing all the data at someone and hoping they're going to find what's important. Don't do that. Figure out what's important and present it in a way that's much more intuitive and tangible to them. You know, if there's one plot here that really matters, just show them that one plot. Don't try to convey all the information in one go. But they are kind of, in some cases, the right thing to do for data that is all real valued and higher than 2 dimensions. Now I should say that you could do the exact same kind of matrix with some of them also being categorical. What we sort of did in the previous sections was sort of cover all possible combinations, right? Real, categorical, and categorical. So you can have similar things where you actually, you know, some of these would be like box and whisker plots, some of them are scatter plots, and some of them are heat maps of some kind. That would be how you have a scatter plot matrix. It's not that well supported, but you can generate these things for multiple, you know, higher dimensional data where it's sort of a mix between categorical and real valued data. I'll show a few others people use as well, but that's, you know, a perfectly valid thing to do. Okay, just a few more things to mention, and then we're going to be about out of time. Another way of doing this is via a different view on this is via a bubble plot. So you can, instead of sort of doing a 3D plot, you have a different feature. You plot a 2D scatter plot, but then have a third feature of the data that changes based upon the last category. So if the last category is real valued, I could change, for example, the size or the color of the data points. The color in particular is quite useful in the case that you have one feature that is actually nominal valued, right? If you have a nominal valued third feature, it's very reasonable to do a scatter plot over the first 2, and then something like color coding the third one. So you see this all the time in like machine learning classification, where there's always kind of there's always a categorical variable, the class of the output, but the features themselves might be real valued. So plots like this are very useful in that case because I can convey actually 3D information here. These are, you know, the color here is the third dimension, but because it's just a categorical assignment, there's no real issue of confusing them or not quite finding the distinction or not being able to interpolate between colors well. They're just, everyone can tell what's green there and what's blue. Okay, so the last thing I want to mention is that in this class, we're going to extensively use the Matplotlib library for plotting. So it is sort of standard for plotting in Python and Jupyter Notebook. And by default, though, the figures look pretty ugly by default. They're getting better actually at that. This was from a few years ago, and since then they've improved. But I would still actually import another library like Seaborn to make figures prettier. And I'll mention how to do this in the notes, or I'll put the notebook up of how to do this. I showed this a little bit, but it's important to emphasize that Matplotlib is really aimed at generating static plots. There is the ability to interact a little bit with these things. You can, you know, have this plots you drag around, stuff like this, but they're really meant for static plots. It's not meant for data interaction. And I should say that there's a number of other libraries that are, might be better, but they're not nearly as common. This is still the de facto standard. So if you give me 1 minute right now, I just want to highlight the fact that all the figures I had there are easy to create in Matplotlib. Here's a Jupyter Notebook where I basically import Matplotlib. This is just a bunch of sort of boilerplate that you can use or not. But then you can do things like bar charts with plot.bar, pie charts, but I should not even tell you this command. Seaborn actually doesn't even include this command. It leaves it out entirely. Things like histograms, scatter plots, line plots, etc. I'll describe those more in the notes for this lecture, and I think we'll just move on next lecture to talking about vectors and matrices.